Okay, I want to create a new project. This time I want to practice using the X, Y, and Z 16-bit registers to record, read, and write data. So what we can do is create a table of data in our program memory, read the data using the LPM instruction, the load program memory instruction, and then write the data to SRAM memory. So first, we'll start off with a new project using the Atmega 328P. So I'm going to create a new project here. If you open your AVR Studio, you should have a window dialog box pop up so that you can create a new project. So that will look like this. So I'm going to call this indirect addressing is the method we're using. So indirect address, and I'm going to create a new folder for it. And so this should work on any microcontroller. I'm just going to use the Atmega 328P. Here it is. Okay, so if you did everything right, you've got the registers, the I/O addresses on the right-hand side there. And typically we should put some comment up at the top indicating what the program is for and your name on it. So okay, and then we want to include our include file so that we have access to the names for all of our registers. So the include directive, M328pdef.inc, and we'll put a no list in front of that so that we don't include it in our IO or our listing file. Then we'll continue listing after it. Okay, so let's define our temporary register. And for now, we'll start off with a .org reset vector. And for now, we'll just continue to we'll set our stack pointer. And so on the Atmega 328, so we have the high and low byte for our stack pointer. You can see them on the right hand side over here. So we need to output the high byte of RAM end to SPH. And then the low byte of RAM end to SPL. Okay, so what we're going to have is a table, and we'll use a label at the beginning of our table and the end of our table. And those labels will contain the address for the first value in our table. So for now, let's come down here and create a main function. And then we'll have a table of data here, and each row in our table we use a directive called defined by .db, and that will allocate space in our flash memory, in our program memory, to store the data for our table. So what we can do is we could go ahead and get a table of data to put in there first, and then we can set up our registers, X, Y, and Z registers. Those are the 16-bit registers. So register X is R26 and R27. Register Y is R28 and R29, and register Z is R30 and R31. So we'll use all three of those addresses. We can use the Z register as an address for the data that we're going to read in our program memory. We can use the X register as an address for our SRAM memory, to where we want to store the data. And we can use the Y address to compare with the Z address. So we'll set the Y address originally up to the end of our table, and then each time we use the Z address with the LPM instruction, we'll compare the Y and the Z, and if the Y is equal to the Z, we know we got to the end of the table. So let's first go get our data. So I have a document. So if you note the address, this is on my GitHub account. GitHub.io supports web pages, so I made a few little web pages, and these are interactive Python documents that I exported from the Jupyter notebook, or interactive Python notebook, which is an awesome notebook for a programming environment in Python. So I wrote some Python code to generate tables of data. So I clicked on that for a second. So this is a Python code in an interactive notebook. It's all free software that you can use. It's called Jupyter, Jupyter notebooks, if you're interested in downloading it and using it for Python. So I've got here a table of data that I set up for servo motors. So the servo motor I tested on the bench with a signal generator and a oscilloscope, and I was able to get a pulse width to the motor. The larger the pulse width, the further the motor turns to one direction. The smaller the pulse width, the further the motor turns to the other direction. So I tested the motor on the bench to see what the maximum and minimum number of microseconds I could have for the pulse width. So I got 2,350 microseconds as a maximum on one travel on the motor, on this particular motor I tested. 450 microseconds is a full travel the other direction. So what I did is I wrote the Python code here to generate the tables of data that I can load into my output compare registers on a PWM, a pulse width modulated signal, and it will output pulse widths of these number of microseconds. So 2,350 microseconds, which is 2.35 milliseconds. That was full travel one way on my motor. Then if I had the pulse down to 450 microseconds, which is 0.45 milliseconds, that was full travel the other way. So I determine those on the bench. I'm not really teaching a Python class here, so I'll just kind of skip through this. But you have the address, which was harrimand.github.io, if you want to come up and look further at these. So the data, this table here, pulse widths, is a table with 200 pulse width values, and so the pattern on the servo motor will be a sinusoidal motion from left to right, and then so I've got and I plotted the data here so you can see the sine wave, and notice it starts off at about 1400 microseconds. So that's the number of microseconds. And then it goes up to, what was it, 2350 or about there. So what I wanted was a table of data that we can add or subtract to our output compare register, and that will change the pulse width on our PWM signal to the servo motor. So first I created a sine table with 200 values. The reason I chose 200 values on this particular table is if we're updating the servo motor every 20 milliseconds, that's 50 times per second, which is the frequency of the updates that the servo motor expects. That's the way they're designed. It'll take about 4 seconds to complete all the way through this table. So this is a 4-second sweep on this table here. So what I did was I took the sine table and I calculated the step size to go from each step to the next step in the table. Then our microcontroller can read those values and add or subtract them from the current value in the output compare register, and then that will update it to the new position. And when it sweeps through those, the servo arm will swing back and forth in a sinusoidal motion. So I calculated all the step sizes and then I converted them. So these are positive and negative numbers. I converted those to a signed 8-bit number. So when you add a signed number, if it's from 0 to 127 is positive, and then you go from FF down to a 128, that would be the negative values. So the most significant bit on the signed number is a 1 if it's a negative value. So I took these values here are signed 8-bit numbers, and I converted those values to hexadecimal values. And so this table here has a label at the beginning of the table. See the colon at the end of the label name. And it has all of the data for the table. And so these are signed numbers. So when you add a number that is a negative number, of course, it'll be equivalent to subtracting the number. So I'm going to copy this table here and go back to our program, and I'm going to paste this table here, and just like that we have a table of data. So we can copy this table into SRAM. There's 200